Welcome you all to the CFD workshop in OpenFOAM. So, this training is aimed to be a beginner's level training session, and the tutorials or the cases that will be presented will be done in the foundation version of OpenFOAM, that is the ORG version, and we will be using version 9 for our simulation. And please feel free to post your queries in the chat. So this tutorial will be looking at the dynamic meshing strategies in OpenFOAM. So when do we need dynamic mesh? So whenever we have a moving boundary or whenever our mesh needs to be deformed along with the boundary, or whenever we need to split our mesh into smaller fractions. In such cases, to accommodate for our moving boundary, we need a dynamic mesh. So in order to know that our boundary is moving, all our domain mesh should know that, should get that information. So for that information to be relayed to all the domain, fluid domain, of dynamic meshing, and dynamic mesh has its own velocity, that is a mesh velocity. So whenever a boundary moves, then the velocity of the boundary is passed to the adjacent cells as well as the other cells in the domain using mesh velocity. So slightly we change our Navier-Stokes equation so that and include the mesh velocity in the NS equations. So when and what type of motions can a dynamic mesh incorporate? So it can be a prescribed body motion. So whenever we move a boundary, like we need to move a boundary linearly, or a boundary, I mean the like it might be a cylinder, it might be airfoil, or it might be in a piston, it might be a moving wall. That is our piston, which when we simulate for the engines, then the piston need to move and deform. So those type of motions comes under the body motion. So and and another when do we need a dynamic mesh? That is when we need a mesh refinement. So in regions where we have like the adverse pressure gradient, or where regions we need to capture the gradient properly and accurately, and in those regions we need a very fine mesh. So in such regions also we can use dynamic mesh strategies to split only those regions, like the areas where we need to accurately resolve our flow. So in such cases also we can split the mesh into smaller regions and refine them using dynamic mesh. And it is also used in fluid structure interaction whenever the structure moves and it interacts with the fluid. In such cases also we use dynamic meshing strategies. So in OpenFOAM we have different type of dynamic mesh strategies. Those are mesh morphing, adaptive mesh refinement, overset mesh, and adaptive mesh interface. So mesh morphing, it means the physical deformation of the mesh. So we can see that the mesh is being deformed, or it is displaced, or we can see its deformation physically in mesh morphing. Whenever the boundary moves, then the adjacent cells to the boundary, they also deform along with the moving boundary. So this comes under mesh morphing. And adaptive mesh refinement, like I said, whenever we need to refine our mesh in on only certain regions, then we can use AMR. So this is a very interesting topic. Like we don't want the refinement to be in all over our domain. So only in those regions where we need refinement, we can use adaptive mesh refinement. And overset mesh, this uses interpolation techniques. So we don't see the physical deformation of the mesh. The mesh does not deform physically, but the deformation is passed to the cells using interpolation methods. And another one is the adaptive mesh interface. So in this AMI, we have static region and rotating region. So between the static and rotating region, an interface is formed, and between that in that interface, between the rotating region and the static region, interpolation takes place. So the rotation of the boundary is interpolated to the static mesh, and vice versa from the static to the rotating mesh. So in this way, there are dynamic meshing strategies in OpenFOAM. So today we will be looking at mesh morphing. So mesh morphing means the mesh is deformed and diffused from the moving boundary. So when the boundary moves, then the mesh is deformed, and the mesh motion is passed to the fluid cells. So that is controlled by mesh diffusion. And motion can be predefined functions or tabular data. So the motion can be either predefined functions, or we can also provide a tabular data, so how our boundary moves. So we can provide that using functions or tables. And for large displacement, the boundaries, our mesh quality will decrease. So we need to uh, look for we need to consider the CFL number and monitor it while we are dealing with a large displacement boundaries. So for large displacement boundaries, mesh morphing might not be a proper method. So we need to shift to other methods like overset methods for large displacement boundaries. So today we will be looking simulating a transient incompressible laminar flow across an oscillating cylinder. So I have provided here the dimensions of our domain. So the velocity will be 2 meter per second from the inlet, so that our Reynolds number is 200, and diameter of the cylinder is 1 meter, and the oscillating amplitude is zero point 0.5 meter, and the oscillating frequency is zero point 0.5 hertz. So actually, this is a case study done by an intern, and this case is available in FOSSEE website. So I'll show you where we can get this case, and I've used the same case in this session. So there will be a slightly different structure for dynamic mesh case. So we need to add two files in our case folders. That would be a dynamic mesh dict that controls that controls like which is the libraries to be used in for our dynamic mesh motion. So for the mesh motion, we have various libraries. So we uh, assign it in dynamic mesh dict. And the point displacement is like how our boundary moves. So is it oscillating, or is it linearly moving, or is it rotating? So such motions are prescribed in point displacement file. So let's begin our uh, setup. So before moving on to the case setup that to this case that I have shown here, so let's see how we can uh, give how we can from scratch how we can simulate we can set up our case. So we will take a simple tutorial from our open form case, and then we will try to develop that case into dynamic mesh uh, case. So let's go into our Ubuntu folder. And inside the Ubuntu folder, our tutorial cases are located in OPT. So I'll be using OpenFOAM 9 version. So, and we can see there is a folder called tutorials. And from tutorials, we'll get inside incompressible. And let's take a tutorial case from pimple foam, laminar. So mm, we can take any one case. We can take from icofoam. Okay, let's take a cavity case and see how we can set it up as a dynamic mesh case. So I'll copy this cavity case from the tutorial to my uh, working directory. So let's copy it here. Now I'll be opening my terminal. So I'm using OpenFOAM version 9 to simulate this case. So let me open the case in VS Code. So we can see that this is the case for static simulation. So this is not dynamic mesh simulation. So this is the tutorial for static cavity case. So looking at the block mesh dict, we can see that there are different boundaries. So there is the name is moving wall, but in this case, the wall does not move. So this is just named as moving wall. So we will try to move this wall as the name suggests. So we'll try to move this wall, and there are other boundaries also. So let's first open this in a paraform to see what are the boundaries. So okay, let's create our mesh. So the mesh creation will be done by block mesh command. So after we type block mesh command, we will get the folder will be generated called polymesh. So inside polymesh there will be boundary and what boundaries are present. So after block mesh, we can see polymesh folder is created, and inside it we can see the boundaries, the boundary file. Now let's see this in Paraform. So this is our domain, and if we see then the upper wall, this is the moving wall that the boundary named moving wall, and these are the fixed walls, and these front and back we have empty. We are dealing with 2D simulation. So now what we want to do is we want to move this plate. So we want to move this plate using dynamic mesh strategy. So for this plate to move, we also want this fixed wall. So we also want this left and right wall to move along with the upper plate. So if the upper plate, that is the moving wall, moves, then these two right and left plates should also move. So we can't keep this as a fixed wall because our plate at the top is moving, and that will also create a mesh motion for these right and left walls. So uh, we will make a separate boundary for this right and left walls, and this bottom wall will assign a different boundary name. So let's do that first. So what I mean is, so in the block mesh dict, we have assigned the three walls under the name fixed walls. So these three walls is under the name the boundary name fixed walls. So we will uh, divide that into two groups. So let's classify is at moving walls. So the left and right walls will keep it as moving walls, and we will then the bottom wall will keep it as fixed wall. So this fixed wall is our bottom plate. So we have here three boundaries, three patches. So we need to delete two. Now which one to delete? So if you turn on the axis grid, so we can see that the bottom wall is the patch where y is 0. So y, you can see that the y in the y dimension, this is bottom plate. We have at 0 coordinate. So if you look at the vertices, then which of the vertices have 0 y coordinate? So it is the first one, this number one vertices, and then we have number two vertices, and then 3, 4, and the fifth one, and the sixth one. So sorry, this is with 0, 1. So we start our naming from 0 in our block mystic 0, 1, 2, 3. This should be fourth, and this should be fifth. So our bottom patch is made from the vertices number 0, 1, 4, and 5. So this one will be our bottom wall 01540 or 0145. So we delete these two from our fixed wall, and we delete from the moving walls, we delete this bottom wall. So I hope you are getting what I'm trying to do. Now let's again do block mesh. Okay. Okay, now I have again run the block mesh. Now we can see that there are four boundaries formed. So the one is a moving wall that we will be prescribing a body motion to the moving wall, and the moving walls that were the left and right wall patches. And this is the fixed wall, that is the bottom wall, and front and back as empty. Now if you reload this file, okay, let's open Paradigm again. So now we can see that the moving wall is the top wall, and the moving walls are the left and right walls. That also moves along with the moving wall plate, and the fixed wall is the bottom wall. So I hope we have like divided our domain into three into different divisions again, four now there were three boundaries, now we have four boundaries. Okay, now after that, let's set up the boundary condition. Now we have our boundary named boundary naming properly done. Now we will set up the boundary conditions. So you can see that for the boundary conditions of view, there is only moving wall, because in the tutorial case we didn't have other boundaries. So what we now want is we want to set up the boundary condition for the boundaries that we have created. So we had created moving walls, and then other boundaries were fixed wall. So let's make it fixed wall. So it's fixed wall. And for the fixed wall, we want no slip boundary condition. That's fine. So or we can also, this is also no slip boundary condition, fixed value 000. So we can also, instead of no slip, we can also use this boundary condition that is equivalent to no slip boundary condition. Now for the our this tutorial case. So the tutorial case, the moving wall was fixed value, but we don't want we want our wall to move. So we won't require this boundary condition. We will have to use another boundary condition, that is moving wall velocity. So this is the boundary condition that is used when that is the important boundary condition. So we need to, whenever a boundary is moving, then we need to assign this boundary condition. So this is not a no slip boundary condition. So whenever the adjacent cell to the moving boundary will get the velocity of that boundary. So this boundary condition does that. And then moving walls, let's keep it as a fixed value for now. So this is our moving plate. That is the upper plate that we are prescribing moving wall velocity. So actually, this in boundary condition in this U file, we will not prescribe the motion of the boundary. The boundary motion will be prescribed in point displacement file. So here we have not yet set up the point displacement file. So let's first set up the point displacement file, and then another file we need is the dynamic mesh dig file, which we have not, which we don't have here right now. So we have only the transfer properties file and all these files. So what we can do is, so let's again go to our Ubuntu and our tutorial case, tutorials, and then let's go to incompressible, and pimple foam. So here is a tutorial case called wing motion. So from that wing motion, you can just take those files out from these tutorials. So constant, there is a file called dynamic mesh dict. So let's copy in our constant folder dynamic mesh dict. And another file that I said would be required was a point displacement file. So it's here point displacement file. So let's also copy this inside our zero folder. So this is our structure that I said. In our zero we need point displacement, and in constant we need dynamic mesh dict. Now first, before setting the boundary condition for UP, like the solver settings, will just set it up for dynamic mesh dict. So we can see that these are the libraries that we use. So this is dynamic motion solver FB mesh. So if you want to see where these solvers are located, or where these libraries are located, then you can just go to the OpenFOAM 9. So inside the OpenFOAM, inside of the case directory, you can see a folder called SRC. So inside SRC, you will see a folder named FB Motion Solvers. So you can see FB Motion Solver, and inside FB Motion Solver, you can see the folder FB Motion Solver. So these are the solvers that are available for our dynamic mesh motion. So these are the motion solvers for dynamic mesh motions. So inside displacement also we will have different type of how do we solve the displacement. We use the Laplacian approach, or we use SBR stress approach. So right now we'll be using a Laplacian based approach to solve for the mesh velocity and mesh displacement. So we'll be using displacement Laplacian. So in our constant and dynamic mesh dict, let's see. So these tutorial case that we had that we copied from the wing motion inside pimple foam. So this tutorial case used 62F rigid body motion. So if you want to see where that file is, so you can see that it's in the 62F rigid body motion. So this is a different solver for dynamic mesh motion. This is a different solver, but we won't be using this solver right now. We'll be using a simple Laplacian solver, so which is located inside FB motion solver. So first of all, what we need to do is we need to change this library. So we don't use this, so we use library name FB motion solvers. So this solver FB motion solvers, and inside FB motion solvers we will be using displacement Laplacian. So motion solver, our motion solver name would be displacement Laplacian. So right now we don't need these, so let's delete this. If you go inside displacement Laplacian, so displacement Laplacian solver, first of all, before as this class is generated, it will initialize with displacement motion solver. So this displacement motion solver class is located in another folder again. So if I duplicate this, then you can see that this is the base class is located inside the dynamic mesh folder. And inside dynamic mesh folder, we have a folder called motion solvers. And inside motion solver, we have displacement. So displacement motion solver is located here. So this is the base class. So from this, it is calling displacement motion solver that is displacement solver constructor. So we go into this, and the displacement motion constructor, displacement motion solver, this is the class, and this is the constructor. So this constructor again calls another constructor called points zero motion solver. So the point zeta motion solver is already again located in another like so here it is located here point zeta motion solver. So if you open this file, then you can see that ultimately a motion solver, the motion solver is called. So motion solver constructor is called. So uh, so here we need to go again. Now in this this is the file that is ultimately referred to. So we can see that what do we require is we require the coefficient dict. So inside the dictionary dynamic mesh dict. So dict means dynamic mesh dictionary. Already copied this dynamic mesh dict file here. So this is the actual dictionary, and inside this dictionary, there it searches for optional subdict. So subdict is what we dictionary that is created inside the main dictionary. So what we need is so if you go at displacement Laplacian one solver, so it is saying it is passing this, and it is saying that we require this coefficient dict function that will return the coefficient dict this coefficient dict variable. And how we define coefficient dict is we set that type plus coefficients. So type means which type the solver you are using. So we are using displacement Laplacian solver. So this is type, and we need to add this string called coefficient. So now what we do is we add displacement Laplacian coefficients, and we create a dictionary again. So this is the sub dictionary. Now after we create sub dictionary, then if we look at this file, so it is saying that inside this will return the coefficient dict variable. So it is saying that look up for the diffusivity value. So we need to again and we need to add a type for diffusivity. So diffusivity means there will be different types of diffusivity. So what are types of diffusivity that is present is we can see in the FE motion solver. So if you go at motion diffusivity, and these are the different types of diffusion. So what is diffusivity is like if our boundary moves, then that boundary motion should be transferred to the nearby cells or to the fluid cells. So how do we transfer that information to the mesh motion or to the other cells apart from the boundary? So that comes under diffusivity. So inverse volume, inverse distance. These are the types of diffusivity. That is uniform. We have another called diffusivity called uniform. So what uniform means is that when the boundary moves, then the all the cells attached with the boundary, that is from the nearby adjacent cells to the outermost cells, so they will get a uniform mesh motion. That is, the deformation will be uniform. But if we assign inverse distance, then what does that mean is when the distance increases, then the motion of the boundary is felt less by those cells. So the nearby cells will feel the boundary motion uh, heavily, whereas the outermost cells that is far from the boundary, they will feel the mesh deformation, that is the boundary movement, less. So this inverse distance does that. So these are type of how diffusion takes place when the boundary moves. So this is actually that value. So let's set for now let's set as inverse distance. So you can change this value also. So we need the type of diffusivity at inverse distance, and this is the exponent, and this is the path from which the moving path. So our moving path would be not cylinder; it would be moving wall. So this is our moving wall. So now this is completed. So our dynamic mesh dict file is ready. Now let's look at point displacement file. So let's go into another important file for a dynamic mesh setup. So that is our point displacement file. So right now we don't have proper boundaries. So let's name them first. Moving wall, moving walls. Then we have another called fixed wall, and other as front and back. Front and back. So let's confirm our boundary name. So boundary. So we see that it's a moving wall, moving walls, fixed wall, and then front and back. Okay. Now in this is the actual file where we prescribe the boundary motion. So how our boundary moves is prescribed in this file. So we can see that. Let me see. So if you go into the dynamic, if you go into the FE motion solver, yeah. If you go inside FE motion solver and inside the point patch fields, so you can see that the different types of motion functions. So how do we want to deform our boundary? So it might be oscillating displacement, it might be oscillating velocity. So oscillating displacement is simply a sinusoidal motion, that is y equals to a sine omega t, and this should the oscillating velocity, that is the derivative of the y. So we can either use oscillating displacement or use oscillating velocity. So apart from this, there are other types of displacement, that other types of mesh motion functions also, like angular oscillating velocity. So this will rotate the boundary. So we don't want the boundary to rotate now, because if in case of rotating pitching airfoil, then we would have used this angular oscillating velocity or angular oscillating displacement. But we right now we just need a linear motion in just one direction in one direction. So we will be using oscillating displacement. So now again back to our point path point displacement file. So what we will set is oscillating displacement. So right now oscillating displacement. And if you go inside oscillating displacement, then you can see that it is asking for amplitude and omega value. The inside dictionary it is looking out for amplitude and omega. So we need to provide that value inside this. So let's provide amplitude and then let's provide omega. Now we need to give a certain value. So what value will be we need to provide? So this will be dependent upon your problem. So how much displacement, how much amplitude you want, and how much omega you want. So right now let's set this as 2 pi, so 6.283. So this can be assigned according to the calculation. So you can calculate these values and then provide. And then another would be 0 point amplitude. Let's provide at 0.04. But we need to provide it in vector form. So in which direction do we want our oscillation of the moving wall? So let's see. So this is our moving wall. So we want in the y direction. So 0.04 should be in the y direction, and 0, and it is, and we can see that we want to compress. If you want to compress the moving wall, then it will be negative y direction. So let's put it as minus 0.04 and then 0. Okay, then our the point displacement file is all set up. So amplitude we need to provide in the vector form, and for omega we have provided in 6 point as this value omega. This is 2 pi by t. So if our time period is if we consider a time period as 1, then omega will be 2 pi. So likewise I set up this value. Okay, then after that, the another important boundary condition would, like with the moving wall, our moving wall should also move. That is, the left and right wall should also move with the moving wall. So we can just we need to provide a boundary condition. This is very important. That is zero gradient. The zero gradient, what it does is it will calculate the mesh motion based on the moving wall. So it because the cells are attached with the cells in the moving walls are attached with with the moving wall, that is the upper top plate. So we need to calculate our mesh motion for the moving walls based on this the moving wall velocity, that is top wall velocity. So we need to provide this as zero gradient, and let's provide fixed wall as fixed value. So we can just provide this fixed value. Control C. We don't want this to move our fixed wall, and front and back we need to provide it as empty boundary condition. So now our point displacement file is also set up. So the moving wall will have oscillating displacement of amplitude minus 0.0 in the negative y direction and omega of 6.283. And the moving walls adjacent that is touching the moving wall, that is the top plate, will have zero gradient boundary condition. And this is also done. Now let's see at the P and U files. So let's set up for the boundary conditions for U and P. Fixed value. So moving wall we have prescribed is as moving velocity. So at the moving walls, you can either prescribe the boundary conditions as zero gradient, or you can also use a fixed value. So this is like a no slip boundary condition. So even though the wall is moving, we'll have two different velocities. The velocity is for the fluid and the velocity for the mesh. So the mesh velocity will be calculated from these dictionary point displacement, but this is the fluid velocity. So we can either keep as no slip, or you can either also use a moving wall velocity for these also. But let's stick to fixed wall right now for this case. And fixed wall we need to provide 0, 0, 0. So we don't want any velocity from this wall. Okay, now let's look at pressure. So let's also add boundaries here. Fixed wall. So we can keep the zero gradient boundary condition for the pressure values. Okay, then let's try to. This case we'll just be looking at the the mesh motion. That is the will not be simulating our case like using our solver. We'll be just looking at how we are setting up the case for the dynamic mesh. In the next case that I had shown you, the laminar flow, we'll be looking at the results also by solving the case. But in this case, I'm just teaching how to uh, start from scratch and then set up the case for dynamic mesh, like what files are required and where do we need to keep those files, and what values we need to what how do we know that uh, what inputs we need to provide. So this first is that case setup. So we'll be just learning how to set up this case, but we won't be running the solver. So there is an important command for dynamic mesh simulations. So that command, the command is move dynamic mesh. So this is the command that just runs the dynamic mesh solver. It won't run our other solvers, that is the fluid solvers like pimple foam, simple foam. After this, we'll just only run the dynamic mesh solver. So if you run this, so you can see that there is an error generated. That is, it is saying keyword pimple is undefined in our dictionary FV solution. So if you go at the FV solution, then it is searching for pimple algorithm, but we don't have it defined yet. So what we can do is, based on our error, we need to debug the error. So let's go again to our tutorial case. So let's go to tutorial case. Let's go to the same tutorial, pimple foam and wing motion. Let's go to our FV solution. So it was saying that pimple is missing there. So let's just copy this out. from our missing case. So I think the it won't it is not recognizing piezo solver. So let's make it pimple. Then after then let's again try to see what we get. So it is saying keyword cell displacement is undefined in dictionary FB motion solution solvers. So again, it is saying that we need to, because we are solving for cell displacement. So how do we want to solve the cell displacement? We need to provide in our FB solution. So let's copy this. Control C. Let's copy it in our case. Control V. So I think this will be done. So let's again try to run. Okay. Now you can see that our dynamic mesh is run. So let's run it for some more time. So this we can change the time in our end time in our control dict. So end time, this is not one. So this is the our case. So inside control dict, we can see that our case is set up for 0.5. So let's make it 1 second. So we had, why I'm giving it as 1 is because we had said that we had calculated omega based on time period of 1. So after 1 second, the piston comes back to its original position. So that is how that is the time period. So based on that omega, I kept time period as 1, or based on our time period, we can calculate omega. Okay. Let's clean our case first, because the case is already done. Just to clean our case, we can type this command. So foam clean tutorials, and then again let's run our. So after cleaning the case, the block mesh should again be run, because the polymesh folder will be deleted. So after block mesh, let's run move dynamic mesh. Let's run for 1 second. Okay. Now let's see. RF foam built in. Now you can see that the mesh motion is taking place. Now you can see that the how the boundary has been deformed. So if we look uh, so if you look at the cells, then these cells sizes are being changed. So this is what I mentioned mesh morphing. So if you look at the first beginning before the simulation starts in 0.1 second, so the cell height is larger compared to, and it starts and it keeps on decreasing. So you see that it's now increasing. So as we are expanding, so this is increasing. So this is what I mentioned mesh morphing. So right now we'll stop here, because we don't want to solve this case, because this case requires a compressible flow solver, because we are compressing the fluid. So we can't solve it using a simple pimple foam or simple foam icofoam. These are incompressible solvers. But right now this solver requires a density based solver or the compressible flow solvers. So we'll stop here for this case. This will be a different case. So but our main focus here is to how we can set up a case starting from a tutorial or a scratch, and then building it up as a dynamic mesh case. So how we started from a tutorial case from cavity, and then we made a case like a piston simulation. So this is the same strategy that is used in piston simulation, and we use a different type of solvers, like we might use combustion solvers, or we might use other compressible solvers for our case. So right now I'm stopping this first case here, and let's go to the next case, that the main case that we are about to simulate. So the next case is uh, the oscillation cylinder case. So first of all, I'll show you where you can get this case. So you just go to uh, cfd.fossee.in. And inside, you can go inside case study project, completed case studies. And I think the case number is 44. So the case that I'm about to present is available here. 44, yeah. So this is the case. Laminar flow corrosion oscillating cylinder. So if you want to simulate in your system, then you can just download this case and then you can simulate it. But there are slight changes that are being made in this case that I'm going to present. But the solver setup is same. All everything is same. Just I've added how to calculate the force coefficients, and I have simulated for a longer period of time. So the end time in this case that you download is just I think it is 2 seconds. So you can run it for a longer time. So I've run for 4 seconds. So you can even run for a longer period of time till you get steady results. Okay, now let's see this case. So likewise, like we are set up, this file also contains point displacement file. So this is the same, and this file also contains dynamic mesh stick file. So this it has also used a motion solver called displacement Laplacian. It has also used inverse distance. So you can change this. You can change it to uniform. You can change this to inverse phase distance or any other. You can try different type of diffusivity and how the mesh deformation changes based on the diffusivity type. So you can try it out on your own and see how these type affect your mesh deformation. And the point displacement, the file is the same. So it has provided, I think, it has also provided oscillant displacement for the cylinder. So the cylinder will move up and down based on sinusoidal motion. So the omega is 3.14. This amplitude, this value is calculated based on what you want to achieve or dependent upon your problem statement. So this will be variable in different cases. So likewise, the inlet, the outlet, and cylinders. You can see that the type is moving velocity that we had also used. So this is the moving velocity, and I think yeah, net outlet. So yes, this I've already simulated this case. So I've ran it for about 4 seconds. So because this will take some time, so I've already ran this case. So let's visualize the result. There is no much difference in our case that we are set up in this case. Only the difference is the domain and the like. If you see, you can see first. Let's see the domain. So this is the domain. So you need to learn how to create such type of domain. So you need to see at the block mesh dictionary. So I won't explain how to create these domain, but you can see inside system block mesh dict. So how this domain is being generated. So we will be using different blocks, and by using arcs we can the different type of blocks, and then we need to use arc. So to define the circular arc. So to define the shape of the cylinder, we need the arc feature. So and these are the boundary names in block mesh dict. These are boundary names. And in the control dict, I have ran it for 4 seconds. And what I've added is I've added the function called the force coefficient. So what this does is we can calculate CDCL based on this force coefficient function. So we don't need to calculate manually from the view or from other type of code. So these are the inbuilt functions that is available in OpenFOAM. So just you need to give appropriate values. So our pass name is cylinder, so we need to change it to cylinder. And after that, the important parameters are drag direction based on your domain, what direction for drag. So we can see that our drag direction is X in X direction, and our lift is in Y direction. So based on that, I've kept it as here. And after that, this is the free stream velocity. So our free stream velocity is 2 meters per second. So as we have provided here in this figure. So after that, another important would be the area reference. So this will be the planform area for cylinder. So we can see that our domain is our this diameter is 1 meter, 1 meter, and in the z direction. So area, how we calculate the area is we calculate the area based on the planform area. For the for the airfoil, it would be the planform area, that is from the how we look the airfoil from the top direction. So based on the chord length into the z direction in block mesh. So this is the z direction in block mesh. In our block mesh, our z direction is one, I guess. So let's look at block mesh. Yeah. So you can see that the jet direction is it starts in jet from 0 and ends at 1. I think so. So based on this value, I have kept the area reference as 1. So this is this parameter is very important, area reference. So you need to keep appropriate value to calculate accurate CD. Okay. So after that, I think you know decompose part dict. So decompose part dict is dividing the domains into different processors. So as we skimmed an episode, we won't touch this much now. Like we know that we need to provide for the cell motion and cell displacement. So when do we need cell motion? That is when we are using instead of displacement Laplacian, if you want to use uh, velocity Laplacian solver, dynamic solvers, and then you need to assign cell motion also. But we right now we don't require this, but this is also set up. So but in displacement Laplacian, we only want to include a cell displacement inside epi solution. And likewise, I say we have seen that piezo is somehow not working with dynamic mesh. So we need to it asks for pimple algorithm. So we provide pimple algorithm also, and the selection factors, these are for the solver convergence and stability. So there are not many difficult parameters you need for dynamic mesh simulation. So just you need to add what is the required, but to to get accurate results, you might need to change different parameters. Might to change solvers or other things. So this will depend based on how much accuracy or how much if a result are properly validated or not. So you might have to check out different solver settings also for like for the cell displacement and other things. Okay, so I think these are the files, constant dynamic mesh transfer properties. So we are using laminar. Sorry, this is for the kinematic viscosity. So kinematic viscosity value is used based on like density. That is dynamic viscosity divided by density. We get kinematic viscosity. And turbulence properties, we are using laminar. So I think that's done. So if you want to see these are the boundaries, faces, neighbors. So these are the information of our mesh. Yeah, after look, then let's see the results. Okay. Yeah, I think this is the result for that. So okay, I'll open para view. So you can just open para view if you have if you have installed externally, then you can just open para view and drag the form file. So you need to create form.form file .form extension, that is touch form.form. You can just go in a terminal and then type touch form.form. So you will be creating a dummy file for the paraview. So this will be enough to load in external paraview also. So we can see that we have not reconstructed our case. This is a decomposed case. In all the files are all the time folders are located inside the processor. So we have the privilege of just selecting decomposed case in paraview. Okay, now let's see at velocity. So you can see So if you want a steady wake behind behind a cylinder, you need to run for more time. That end times will be much larger. But I have only ran for the first 4 seconds. So this is the end time for just 4 seconds. So what another uh, important parameter or important what we call important field is in this type of oscillating cylinder is the vorticity. So you need to know how to visualize vorticity in paraview. So just go to filters and alphabetical, and you can look at gradient. So there is some filter called gradient of structured data set. Let me see, gradient of structured data set. Okay, I think this is the gradient. Now you can see gradient, and now the gradient is calculated based on velocity. So you need to select velocity here instead of u, and you need to click compute vorticity. So just you need to click this and click apply. And in the drop down, you can now see that a vorticity field is also generated. Like velocity field was present, now vorticity field is also present. So you can see now we can see the vorticity. So vorticity is just the call of our velocity. So now, so you can see that vortex shading is happening behind the cylinder. So you can see the one common vortex are formed. So you can to visualize it more. You can just go in this customize, what is this called, rescale to custom data range. So you can just rescale like to some lower values, so that you can visualize it more properly. So you can see that the color is increased. So you can just reduce these numbers. This is just for visualization, proper visualization. This will not affect our values. So this is just to keep to make it more aesthetic or something, like if you want to look where where the vorticity is very higher, like if the range is very large, then we can't see the differences more clearly. So we can reduce using these custom data range also. Yeah, this is like you can also now, if you want any values, then you can just plot along the line, or you can plot along so there is a feature for the plot along line. So you can filters alphabetical. So plot data over time, if you want any data to plot over time, or if you want to plot over line, so you can do this post processing on your own. And another important that we had created, what if you want CD and CL, then we can see that our CD and CL are now being stored in post processing folder inside force coefficients. So you can see now we can see that we have created a file for storing or for writing CD and CL. So 6671. Yeah, this is the CD and CL. Now, if you want to plot this, then you can just do it. So just rename it as proper, keep it proper name. Let's name it as time. Let's name it as CD, SCL. Now let's save it as Excel file, not as a .dat file. So let's save it as Excel file. Since so now you can see that our Now we have created a force coefficient Excel file. Now let's, I think I have one cavity. Yeah, I think I have uh, one Python code to plot this. So let's see how the plot comes out to be. So this is the plot. So first coefficient is Excel axis, and so let's plot this. Plot day after time. Yeah, sometimes if we convert this, then this is in the Excel file. Oh, so it is df dot small. So our time. So yeah, you can plot these things on your using any. You can also use Excel or you can use Python to plot these values. So let's first plot without any. So here we can see that let's plot from 0 y limit 0 minus 5 to plus 5 y limit. Okay. So this is just the, so if you know the simple Python, then I think you can understand what I'm doing. So I'm just defining the X and Y range where I want to plot because the Y range was very, very high. So we were not able to see the oscillations or the amplitude of our curve. So that's why I'm decreasing the ranges. Okay. Yeah, so in this way you can write the first coefficient and then plot value. You can find Stroll number and other post-processing results. So you can post-process the results deep because the main you if you want to validate and your case, then you the important parameter is CD and CL. So you can just use first functions like first coefficient functions and calculate CD CL. So these are available inside OpenFOAM that are inbuilt functions. So and you can post process based on like plot the results based on Python, or you can also use Excel to plot the results. So you can also visualize the streamlines and all those parameters, all those post processing parameters. So you can do it on your own. So these are uh, the important these are required small things that you need to set up a dynamic mesh case. Now, for the accuracy, you need to properly validate and you need to change different solver settings, different you need to change the motion diffusions and all those things. But this is a brief this is to briefly show how we can set up a case from a scratch and then start building to a oscillating cylinder case or oscillating airfoil case or a combustion or a piston simulation case and all those complicated cases. Yeah, so this is from my side. So thank you everyone. So if you have any questions, then you can ask.
Sir, during the presentation of this case and for the other cases which were presented earlier, it was
Yes.
said that some dictionaries are not available, so they have to be imported from other test cases. So how do we know exactly which ones have to be imported from other cases?
Yeah, so you mean that I imported these dynamic mesh ticked and point displacement file. So you are asking from how do we know that we like import these files? You're asking that.
Yeah, yeah, yeah.
So actually, you can like so like I have already like if you want to set a case, then you can see that in the tutorials case, you can see that under incompressible people from RS. So there is a tutorial case for wing motion, right? So this
Hmm.
is the tutorial case, and this is a dynamic mesh case. So you can just look at this structure, this is because this is pre-available in OpenFOAM as tutorial case. So you can look this structure and then uh, and then decide which cases, which dictionaries you need to use. Like we need dynamic mesh. So this is the important dictionary, and this point displacement dictionary. So if you want like another so if you want to use velocity Laplacian, then you will be requiring point motion ux files. So for that you need to look at the solver. So what I'll show you where it is located. So if you go at src dynamic mesh, and then if you go inside motion solvers, and you can go inside displacement, and you can go inside displacement and the source file. Yeah, you can see that you need an object called point displacement. You can see in this source in the .c file. So you can see that you need to create an object that must be read. So must read means you need to read that object, and you need to it is auto write means it writes on its own. So you need this object to be created. That is this dictionary you need require. So you can see, and now if you want velocity Laplacian solver, then let's say go inside velocity and velocity motion solver. Now you can see that you will be requiring a file called point motion u file. So these are different dictionaries that will be different based on your uh, dynamic mesh solver. So I think you got it, what you want to ask.
Yeah, and also, sir, I'm currently trying to simulate something similar to motorbike test case, but
Hmm.
I'm trying to include the temperature of the air in it. How can I do that? Because the original file does not have the temperature, or is there any other test case I can use for that?
Yeah, which solver are you using for this simulation?
That I'm still thinking about it because I think pimple foam does not include temperature in it.
No,
It's
no,
only an incompressible solver.
pimple foam includes temperature.
It doesn't.
Icofoam solver does not include temperature. I think
Hmm.
pimple foam includes temperature. But let me see. So if pimple foam do not include temperature, okay, then you can use raw pimple foam if you are using compressible solver. Then. So if you go at tutorials and then compressible and raw pimple foam, then I think we will have you will be including a temperature file.
Yes, yes, yes. Okay. Thank you, sir.
Okay. Okay. Thank you, everyone.
Thank
Thank
you,
you,
man.
sir.